These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, so let's start by putting this problem in your notes.
So it releases from rest, right? V0 is 0. Okay, so so we have the mass, and we have the height. This frictional mass. It's the same as the 1D motion, right? Should I be using the...
Let's see. Well, I'll tell you what I'd like you to do first is take a minute or two to try this just on your own, so I can see how far you can get that way. If you get stuck, I'll give you some help. But let's start by just taking your best guess for how to solve the problem on your own. If you go off course, I'll give you some help. But to start with, try this on your own. I just want to see where you're at right now.
Okay. Because my mind is somewhere, but I don't see all the things that I need. I'm thinking about this, but then I have this. I don't have that.
Okay, well let me give you some help. Okay.
Oh, should I be using the force like mg?
Let's talk about that. Okay, so I just wanted to get a sense of where you're at. Now we can go through it together. So one thing that's important to realize is that in your physics class, what you're learning is a bunch of frameworks for solving problems. The first thing to do with any problem is decide what's the framework to use. For example, what's the first framework you learned in this class? The first framework you learned is kinematics and projectile motion. That's our first framework in the class, kinematics and projectile motion. Okay. You probably are pretty comfortable with that because you did well on that on the first test. What do you think is the second framework you went over in this course? After kinematics and projectile motion.
To forces.
That's right. Now, forces was the key concept. That doesn't quite say what the framework is. Can you be a little more specific? What's the framework you use for solving most problems about forces?
We first just try to find all the forces on an object, free body diagram. And then from that we could find each force is in the x-axis and y-axis and find the sum of the forces, and from that we could solve pretty much the problem.
That sounds like a good description. We haven't quite named exactly what you're using as your organizing principle there. What I was going for is what you're using is Newton's second law.
Oh, okay.
The framework for organizing all of that is Newton's second law.
Okay.
That's the source of the key equation. For example, when you're doing a Newton's second law problem, what's the key organizing equation that you write down?
F equal ma.
That's a good start. I would write it a little bit differently. First of all, I would say sum of the F equals ma. And also something I think you already mentioned is we have to think in terms of components here.
Yeah.
So really we should say sum of the Fx equals max.
Yeah.
And sum of the force y. So one of the very first steps for a Newton's second law problem is to write down these two equations, and then you use those as your framework. Okay, and you're probably pretty comfortable with that too, because again, that was from the first midterm. All right, now can you identify what was the next framework you went over in this class after Newton's second law?
After that we did uniform circular motion, I think.
You did, that's right. However, it's important to realize that is not a new framework because how do you analyze uniform circular motion? By using Newton's second law. So uniform circular motion, maybe that gives people trouble because they don't realize that. But uniform circular motion is just an application of Newton's second law. Maybe some other time I'll go over that. But that wasn't actually a new framework. Actually, the next new framework you went over was conservation of mechanical energy. That was the next new idea, which is what you wanted to talk about today. Conservation of mechanical energy. Okay, now just like here, we need to know what's the key equation to write first. We need to know what's the key equation to write here first. And the key equation to write here first is this. It's actually a very, very, very simple equation. This is the first equation to write down when you're doing conservation of mechanical energy. Do you know what this capital E stands for here?
Energy.
It would seem so, but actually what it stands for here is mechanical energy. Because in this class, we actually don't look at all types of energy. In this class, we're actually not only dealing with mechanical energy. So it's important to think of this as initial mechanical energy. And then what does this symbol stand for?
So that's final mechanical energy.
Final mechanical energy. Okay, so that's our key equation that we'll write down first. It's so simple, it might look boring, but that's a good place to start. Now, do you know what the word conservation means? What does it mean if mechanical energy is conserved?
It didn't get lost.
That's right. That's a good start. We can make that simpler though. Conservation means constant, right? If something's not lost, that means it's constant. Well, do you see? That's just what this equation is saying. This is saying...
That was something that I had problem with because there's no way that energy is conserved all the time. Energy is always wasted, isn't it? It's always like converted to another form whenever it is used.
Okay.
So how do we say initial energy equal final energy?
That's a good thing to talk about. So in fact, actually energy always is conserved. So how do we square that with what you said? The key is that, remember, what we should say is this stands for total mechanical energy. This means that if you add up all the types of mechanical energy initially, and then you add up all the types of mechanical energy finally, those two additions will be equal to each other. That doesn't mean that individual types of energy can't change, which might be what you were thinking about. For example, one type of mechanical energy is kinetic energy. Is kinetic energy conserved? Well, usually it's not. Usually things speed up or slow down, but the energy that's lost from kinetic energy doesn't disappear, it just goes into potential energy.
Yeah.
So if you add up all the types of energy, it really is conserved. So notice this is not called conservation of kinetic energy, because that wouldn't be true. And it's not called conservation of potential energy, because that wouldn't be true. It's called conservation of mechanical energy, which includes both types. When we do some problems, it'll be easier to see how that comes out. Okay. So on the problems we'll be working on, the total mechanical energy really will be conserved. So what does this capital E stand for again?
Mechanical energy.
Good, except it would be better to say total mechanical energy, because then we can avoid that mistake that we were making a second ago. Now, it's true that there's also even harder problems where the mechanical energy is not conserved because energy is lost, say, as heat. But even then, energy isn't lost, it just changed from mechanical energy into heat. Energy in total is always conserved. So you might have heard that in reality there's no perfect ideal system, there's always some energy lost as thermal energy. But it's not really lost, it's just changed to another type of energy. So if you keep track of all the types of energy, it really is conserved. Now, it turns out that keeping track of thermal energy is actually kind of more advanced than this introductory course would look at this point. So we're going to do simplified problems where there is no thermal energy and there's only mechanical energy. Generally that happens when there's no friction.
Yeah.
Okay. So here's our key equation, and in a moment we'll see how to use this. Maybe we should go on a little bit. All right, so that's good enough, I think, for the time being. So that gives us our conservation of mechanical energy. Okay, so now what's the framework for attacking this problem? Now, one thing you were thinking is maybe I can use Newton's second law. Now, the reason that won't work is because the forces are constantly changing, because this is not a straight slope, it's a curve. Because I made this a curve, remember that when you're doing Newton's second law, you have to break the forces into components? Yeah. But you'd have to do that separately for every single point. Every single point would have different components. So that's probably possible, but that's beyond the scope of the course. That would be too hard for us to use Newton's second law here, because the components of the forces are changing, because it's not a straight slope. For the same reason we can't use kinematics, because kinematics is used when acceleration is constant. But when you have a changing slope, the acceleration won't be constant. It'll accelerate more when the slope is steep and less when the slope is shallow. So these two frameworks we learned earlier in the course, they won't help us for this problem. Fortunately, that's why we introduced conservation of mechanical energy. That can solve problems that these first two can't handle. One of the clues that you should use conservation of energy here was the word frictionless. When they emphasize there's no friction, that's one clue that maybe we should use conservation of mechanical energy. Because if there was friction, remember the mechanical energy wouldn't be conserved because some of the energy would turn into thermal energy. Okay, so let me show you how to attack this. So we have our picture. So the next thing we need to do is write down our key equation here. Well, maybe let's back up and talk about what our key types are here. So let's talk, say, about energy. Do you remember what the SI unit is for energy?
Joules?
That's right. That's good that you know that. The SI unit for energy is joules. Very good. Do you know, is energy a vector or a scalar?
It's a scalar.
That's right. Why does that matter for this class? Well, since this is a scalar, does energy have to be broken into components?
No.
No. That's why I didn't say x here like I did up here. So that's one way that's useful. Also, do we need to choose axes and positive directions when we're dealing with energy? No, because it's a scalar. So that's why we need to know that energy is a scalar, because it changes how we do the problem. Force is a vector, so you have to choose axes and positive directions and break things into components. But energy is a scalar, so that we don't need axes and we don't need components. That's why there's two equations for Newton's second law, but only one equation for conservation of energy. So what are the types of mechanical energy? Can you remember one type of mechanical energy?
Mechanical energy.
What's one of the types of mechanical energy? One type, which I think you did remember a second ago, is kinetic energy. Kinetic energy is a type of mechanical energy. That's right. So one type of mechanical energy is...
I was thinking about electricity, heat, and I couldn't see...
Those are types of energy, but they're not mechanical.
Not mechanical.
Notice electricity is not mechanical, but kinetic energy just involves big objects moving, so it's mechanical energy. So let's review this key concept. Do you remember what the symbol is for kinetic energy?
K.
Good, capital K. And do you know what the SI units are for kinetic energy?
Joules.
Because it's a type of energy. And is it a vector or a scalar?
Scalar.
Because it's a type of energy. Okay?
So that means we never can have negative energy, right?
Actually, it turns out, because it's a scalar, you're saying, that actually turns out to be a misconception about scalars. Some scalars can be negative. Some scalars can be negative. For example, temperature is a scalar, right?
Yeah.
There's no such thing as 5 degrees Celsius north. Temperature doesn't have a direction. Temperature is a scalar, but temperature can be negative, right? You can have negative 5 degrees Celsius or negative 10 degrees Celsius. So that's a misconception. It is possible for scalars to be negative. So it is possible in some problems for energy to be negative. However, it does turn out that kinetic energy can never be negative. Not because it's a scalar, but just because of its definition. So it's not because it's a scalar, but because of its definition, kinetic energy can never be negative. So you were half correct there. Other scalars can be negative, but not kinetic energy. In fact, we'll talk more about that maybe right now. Do you happen to know what the formula is that defines kinetic energy?
1/2 mv².
Excellent. Great. Is this what does the M stand for?
Mass.
And what does the V stand for?
Velocity.
Velocity. Good. So notice when an object, when the object is at rest, what's the kinetic energy?
0.
Good. So, as I said, scalars in general could be negative, but obviously this one can never be negative because the velocity here, because if the velocity was, the lowest can be a 0.
Yeah.
Even if you put in a negative number for V, it would still get squared here. Okay, so it's true that kinetic energy can never be negative. Good. So let's review again. One thing that's very important for these problems is knowing when things are 0. So if something starts from rest, what's its initial kinetic energy?
0.
Good. And if something comes to rest, what's its final kinetic energy?
0.
And if something is changing direction, what's its kinetic energy the instant it changes direction?
0.
That's right. Why is that? How do you know that?
It just brought to my mind the projectile motion right at the very top of velocities velocity is 0. Yeah, y component of the velocity is 0. So I just think
Good.
that should be 0.
Good. So let's try to, that's right, let's clarify that a little. The key thing you're using is, what is the velocity the instant that you change direction?
You have to stop to change your direction.
Kind of. So tell me, what is the velocity the instant that you change direction?
0.
That's right, that's the key.
Okay.
The instant that you change direction, the velocity is 0. But if v is 0, then kinetic energy is 0. Okay, so the formula still works then. Technically, I wouldn't say that you're really stopping, because it's only like for one instant.
Yeah.
The point is, actually, when v is 0, does that mean you're stopped? Not quite. It could mean you're stopped, or it could mean you're changing direction. We just need to realize that a v of 0 either means you're stopped, or it means you're changing direction. When you're changing direction, v is also 0. Because if you're moving in the positive direction, v would have to be positive. And if you're moving in the negative direction, v would have to be negative. The only way you can switch from going in the positive direction to the negative direction is for v to be 0 for an instant. Okay. So in any case, for solving problems, at the instant that you change direction, what's the kinetic energy?
At the instant of changing direction, 0.
Yeah, that'll be important when we're solving problems. It's important to know when things are 0. So it comes back to the idea, the instant you change direction, your velocity is 0. So then the k would be 0. That's all we have to say about that concept for the time being. Now there's only one other, well that's not quite true. There's another type of mechanical energy you've learned about so far in the course. What's another type of mechanical energy that you've learned about?
Mechanical energy.
Besides kinetic energy.
Is it the potential energy?
That's right.
Also mechanical energy?
That's right. Because it also changes when you move. That's right. So potential energy is the other main type.
I was thinking mechanical is whenever something is moving. So whenever something is moving, that's kinetic. But mechanical doesn't...
It also includes potential energy, because potential energy is based on your position.
Okay.
So if you move from one position to another, that changes your potential energy. Another name for potential energy is positional energy. It's based on your position. Well, then the thing that changes your potential energy is when you move from one position to another. So let's be more specific. We'll call this the gravitational potential energy.
So that means only gravity can create that energy?
Well, this type of energy is based only on gravity. That's right. Other types of energy might be based on other forces, but this one's only based on where you are in a gravitational field. That's right. Do you know what the symbol is that we use in this class for potential energy?
I think U.
Capital U. It doesn't seem too logical, but that's what we use. However, let's call it this instead. Maybe gravitational U. So that we know this is the gravitational potential energy. Okay, very good. Do you know what the SI unit is for gravitational potential energy?
That should be joules too.
Because it's a type of energy. And is it a vector or a scalar? Is gravitational potential energy a vector or a scalar?
A scalar.
Because it's a type of energy.
Yeah.
So do we need to choose axes when we're dealing with gravitational energy?
No.
Because it's a scalar.
Scalar.
Okay, good. Do you know what the formula is for gravitational potential energy?
MGH.
That's right. So let's review those. What does the capital M stand for?
Mass.
Good. What does the G stand for?
G of Earth, gravity.
That's what people generally say. That's not the best answer. What aspect of gravity does the little g tell you?
Acceleration.
That's it. So it's better not to say g is gravity, is we want to say g is the acceleration due to gravity. G is the acceleration due to gravity, as you said a second ago. What's the numerical value of g?
Meter per second squared.
Those are the units. What's the number in those units?
Number is 9.81.
Good. So we can say 9.8 meters per second squared is g, the acceleration due to gravity. And then what's the h stand for?
The height.
Good. Now, let me give you an example here. Let's look at this point here. So one thing that's important to realize is this only makes sense if you choose a 0 position. In order to use this, you have to decide what counts as 0 height in your picture, and you can choose whatever you want as long as you're consistent. You can choose whatever you want to be the 0 point. Usually, the best thing is to choose the ground as the 0 point. So here, for example, let's say that this point here is a height of 0.
Yeah.
In that case, what would be the height of this point?
3 meters.
3 meters or 7 meters?
3.
Okay, good. So that was a trap. I was trying to get you to say 7, but you didn't fall for it. Because h stands for the vertical height. So that's the key point I wanted to make here. H is vertical height only. So it's not the length of this slope, it's this vertical height above the 0 point. Okay, good. By the way, you can see then that this is a scalar that could be negative. Because if somehow the object fell down into here, we'd have a negative h, and then we'd have a negative energy. Actually though, if the object was really going to fall down to here, the best thing to do would be to call this the 0 height, so that we can avoid negative numbers. So usually the best thing to do is to choose the lowest possible point as h equals 0, because people aren't very good with working with negative numbers. But if we wanted to be stubborn and insist that this was the 0 height, then we could have a negative energy. So as I said, it is possible for some scalars to be negative. However, we're probably going to try to avoid that here. We'll try to pick an h of 0 that avoids having any negative heights on our problems. Okay, so that's the gravitational potential energy. And you know, you can see why this is called mechanical. Because these are two types of energy that depend on your motion. Obviously, this depends on motion because it depends on speed. But obviously, if you move from one height to another, your gravitational energy will change. So it really does depend on your... Remember I said this was positional energy. Yeah. It depends on your vertical position. Okay. So I think those are the only two types of energy we need to talk about here so far. So now let's move into trying to do this problem. A good thing to always do to start with is, well, so I'll write down this equation, like so. Next thing to do is we have to identify which points on the picture are the initial and the final points. So what's our initial and our final point?
Up there is the initial.
So let's put an I here. And what will be our final point?
At the bottom of there.
Say right here. Why are we choosing those as the initial and the final point? This is a logical initial point because we know something about it. And this is a logical final point because it's what the question is asking us for. But that's part of the skill here, choosing the right initial and final points. Let's also describe those in words. How would I describe this initial point in words? Well, I would say the initial point is the instant the object is released. And how would we describe the final point? We could say the final point is the instant the object reaches the bottom of the hill. You don't necessarily have to write out these words on every problem, but you need to know this in your head. You need to be clear in your head about what the initial and final points are. As the problems become harder, this will become more and more important. Another good thing to do now is to write down what the question is asking us for with a good symbol. What would be a good symbol for what this question is asking us?
How fast? Velocity.
That's a good start, but V final or V initial?
V final.
So that would be a better symbol. So this is a good place to start by writing down the exact symbol that we're going to use here. We know this is the equation we're using, so now we're going to go into this. Well, what's one type of mechanical energy?
Kinetic.
So, and what's the other type?
Potential.
So this will now be our new left-hand side of the equation. It's important to write the general equation first before you start plugging in. So what would the right-hand side look like?
Same thing, kinetic final and potential final.
So we can write that like this. Okay, good. So now we can start plugging in more. So this formula would be 1/2 mv initial squared. And what would be the formula for this?
mgh.
Initial.
And
It's important to put in the correct subscripts here.
Yep.
So how about here?
1/2 mv final squared.
Good.
And mgh final.
Good. Okay. Again, it's important to write the general equation first. People make fewer mistakes if they write the general equation first, but now we need to start plugging in. So what can we plug into this part?
3, 0.
Good. What was the clue word in the problem that said that we were starting from rest? What's the clue word that's...
Because it says is released.
Yeah. So a word like released means starting from rest.
Yeah.
If I had said it was thrown at the top, then it would already have a velocity at the start. So we have to look for those little words. Mm-hmm. So suppose, for example, I said the object was dropped. What would be the initial velocity?
0.
But suppose I said it was shot. Would the initial velocity be 0?
A shot.
Say shot out of a catapult. Well, then the instant it leaves the catapult, it already has a velocity. So words like thrown and shot would indicate that there's already a velocity after it leaves the hand or after it leaves the gun. But if you say dropped or released, it doesn't have any velocity after you open your hand. It takes a while for gravity to give it a velocity. So those are words that can help you to see when you can say something is 0. Okay.
Shot and thrown, you said, right?
In those cases, the object would already have a velocity the instant after it's released.
Okay.
All right. So what's the initial kinetic energy?
0.
If we see that, we could just plug in a big fat 0 for that.
Mm-hmm.
Okay, good. So now what do we plug in here?
3 times 9.8 times 5, is that possible?
Yeah. One thing I forgot to do is we should have said, let's assume this is the 0 height. Remember, you have to decide what the 0 height is, but the lowest point makes good sense. So
And
we'll
it
say that's
doesn't
fine.
matter if we use 9.8 or negative 9.8?
That actually makes a big difference. So in your textbook, this is a symbol they use a lot in the textbook, in italics G. So what does this stand for? Actually, it's just the convention. This, I said before this stands for the acceleration due to gravity, but that was kind of a lie. This does not stand for the acceleration due to gravity. By definition, this stands for the magnitude of the acceleration due to gravity. That's just the definition of this symbol. Whenever the textbook uses this symbol in italics, they mean this is the magnitude of the acceleration due to gravity.
So it's just positive.
So it's always positive by definition. That's right, it's always positive by definition.
So
that doesn't mean that the actual acceleration has to be positive, but the magnitude is always positive, and that's all we care about for this formula.
Okay, so when do we use it as a negative number then? Because
Well,
in projectile motion, we always used it as negative.
Well, even there, I wouldn't quite say that. So suppose, for example, that I throw an object like this. So if I throw an object like this, it's going to follow two-dimensional projectile motion. So then I could write here's my variables. And let's say that I choose up as the positive direction. Well then, what would the AY be? Then AY would be negative g. So the point is, even here, so if the acceleration is negative, then it's not g, it's negative g, because g only stands for the magnitude. G only stands for the magnitude. So if you wanted to say what the acceleration here was, you'd have to say, you couldn't say it was g, you'd have to say it was negative g. That's right. Now actually, usually it's simpler than that, because usually in this class, you don't use g, you just use the number. Most of the time when you're solving problems, you don't have to plug in the variable, the letter, you plug in the number. But so the point here is, g always stands for 9.8 meters per second squared without a sign. It always stands for positive 9.8. That's just a definition. That doesn't mean that the actual acceleration is positive. It just means that g only stands for the magnitude of the acceleration. That's just an arbitrary definition that the textbooks have decided to use.
Okay.
All right. If you decided that you were going to choose down as the positive direction, then your acceleration would be positive g. Right? So, or positive 9.8. So when I asked you earlier what g was, I told you that g was the acceleration due to gravity, but that actually was a little misleading. What I should have said is g is the magnitude of the acceleration due to gravity. That's just the definition. Let's try to see maybe why that makes sense a little bit. Do things, so this is something you might have learned maybe in your chemistry courses. Do things want high or low potential energy? Do things are things like happy when they have a high potential energy or a low potential energy?
No.
Yeah. Actually, actually everything wants to lower its potential energy. If an object is allowed to do what it wants, will it try to increase its potential energy or will it try to decrease its potential energy?
Decrease it.
That's right. For example, if I drop this planar, is the planar going to move up? Well, no, because it wants to lower its gravitational energy. Everything wants, if it can, to lower its energy.
Yeah.
So, when is something happy? Is something happy when it has a high or a low potential energy?
Low.
And when is something sad? When it has a high or a low energy?
High.
So, when the height is increasing, is the object moving in the direction it wants to move or it doesn't want to move?
It doesn't.
It's getting less happy. So should the potential energy be increasing or decreasing?
Increasing.
Increasing. So, should U be a function of positive GH or should U be a function of negative GH? Which way? So we want H and U to move in the same direction, right? We want H and U to move in the same direction. So which of these equations would make
So
H
it's
and
positive.
You need a positive sign here so they move in the same direction. What I'm just trying to show you is this is why what we want to plug in is always a positive number. This only gives us an answer that makes sense if we plug in a positive number for G. If you plugged in a negative number for G, you would get that the higher you are, the lower the potential energy. But that just doesn't match the way the concept is supposed to be set up. So it turns out that it's useful to define G as the magnitude because that's all we really need in formulas like this. If you plugged in a negative number for G, the formula wouldn't make sense. It would say that the higher you got, the lower your potential energy, which doesn't make sense. Okay, so we can actually figure out it makes good sense to always plug in a positive number here for G. And just going forward, anytime you see a formula with a G in it, you should just assume you're plugging in the positive number. That's just the definition of that. That doesn't mean that all accelerations are positive. When you're doing an acceleration, you might have to plug in a negative number, but that doesn't mean that G is negative, it just means you're putting a negative sign in front of the G, so to speak. Okay. So what does G stand for?
The magnitude of the acceleration.
Due to gravity.
Due to gravity.
So it's always positive. Does that mean that the acceleration due to gravity is always positive? No, but G is always positive because it's a magnitude by definition. Okay, so that's a pesky little detail that's good to get worked out. So when you're doing kinematics problems, it's true that you will sometimes plug in negative numbers for acceleration, but when you're doing gravitational energy, you're always going to plug in a positive number for G, so we don't want to confuse those two things. So what should I plug in for G here?
9.8.
Positive. That was the point of that. Okay. So, because otherwise this would come out to be a negative number, which doesn't really make sense. So now we have 1/2. Remember we were saying before, if we choose this as our height 0, this should never come out negative. So let's continue. What can we plug into this expression?
3
times
V squared, V final squared.
We can't plug in a number for this because this is what the question's asking us for. And what will this be?
That will be 0.
Because this is our final point on the ground, where H is 0. Okay, very good. Are you allowed to use a calculator on your test?
No.
No? Okay. In that case, we'll probably actually let you use 10 for G, right? All right, so we should have done.
Actually, no, they didn't let us use 10, but they gave us pretty much 2 times parentheses 9.8. Every number was given us in terms of 9.8 times another number. So we didn't have to use calculator. We could just use whatever number times 9.8.
Okay, maybe maybe it would be helpful if you can then to send me the first midterm so I can see how they're writing those questions, so I can get a feel for that. Okay. Anyway, I didn't set this up to be easy to do without a calculator, so you can feel free to use a calculator if you want. So let's go ahead and finish off the problem. So what do you get?
So it will be 9.9.
Okay, so I got 147 is 1.5 V final squared. So then I got 98 equals V final squared. So then V final. So what's the answer?
I got 9.9.
So what's the answer to the question?
The square root of 98. Yeah.
So what's the answer to the question?
99 meter per step per second.
9.9.
Oh, sorry, 9.9, not 99.
And the units are?
Meter per second.
Okay. Good. Okay, so that's our first conservation of energy problem that we've done together. So you should save that in your notes and then try that again later. So the key thing that I try to do in the tutoring is do all the problems with the same general method, so that we're learning a general method. So all conservation of energy problems should be done pretty much like this. So let's review the key parts. First of all, you have to decide what's the right framework. Well, here's the key 3 frameworks we've talked about so far. We reject kinematics and Newton's second law because the slope is changing here. So the acceleration and the force components would be constantly changing, so these would be too hard. But notice that this is great. This only depends on the initial and the final points. It doesn't matter whether this is sloping or not. That shows you how powerful conservation of energy is. It doesn't care what the path looks like. It just cares about the initial and the final points. And the other clue that we should use conservation of mechanical energy was the word frictionless here. That's often a good time to use conservation of energy. And then the key thing is start with the general equations. So we wrote the general equation, another general equation, another general equation, and we plugged in. And the key here was to find the hidden zeros. For example, the word released said that this would be 0 at the start, and the fact that we're going to the bottom of the slope meant that this would be 0. So the hidden zeros are a key for using this approach. And then we ended up with this. Something else that will be very important is make sure you're clear about what your initial and your final points are. Otherwise, we're likely to make mistakes. We should actually put those in the picture. Okay, do you have this in your notes?
Yeah.
Okay, good. Okay, so that would be a good problem for you to try again. So here is this. I'll give you a different problem. So let's try this problem.
Okay.
So start by putting that in your notes. So you'll have that in your notes.
Okay.
Let me make sure I wrote that right. Confusing myself. Okay, my mistake. All right, what I meant was that this is 7 meters. Okay.
Reduce horizontal below the ceiling. Oh, you want me to work on the
Please.
ceiling? Oh, okay. So you want the V when it is standing right there, like this, right?
That's true. Yeah. Okay. So I'm going to let you work on this a little bit before I give you any help. Try to attack this problem using the same method, same technique, same systematic approach we used for the last problem.
Okay.
If you go off course, I'll give you some help. But to start with, try doing this on your own.
Okay. So start from released. Okay. So initial is 0. U initial is mg h initial. Okay. Final is 1/2 mv Actually, it can be 0 or not, because it is still above the ground. Okay.
Okay, let me give you a little help now.
Okay.
One thing that would have been a good idea, well, so did you write down the initial and the final positions on your picture? It's always good to identify the initial and the final positions.
Okay, initial position is right here.
So let's put an I there. And what's the final position?
The final position is when it is hanging right here, like.
Good. And something that you didn't do at first, but that you should, is to actually draw that. And actually, if you draw that, it's going to look more like this, won't it?
Mm-hmm.
That is, it's going to fall somewhat. It can't be at the same height as before. So this would be a somewhat more accurate picture here.
Yeah.
Okay. So now, what did you, remember you have to choose some point to be your h equals 0 point. So what have you chosen to be your h equals 0 point?
Oh, that's why. Because I was thinking it is above the ground. What about that height? So I can.
What's the most convenient h equals 0?
I will choose 12. I will choose 0 at the bottom of the 12.
Here?
Right at the bottom of
or here?
Yeah, right.
Okay, yes.
Right.
Who cares about the ground? Because we're not going there. The most convenient thing is to choose the lowest point that the object actually reaches. I didn't quite spell this out before, but you get to choose your h equals 0 point. The most convenient thing is choose the lowest point that the object actually reaches. So this is the most convenient point to choose for that here. So one thing that could have helped you here is, although you drew a picture, you didn't draw enough of the picture. You didn't really draw the final position. So it's always good to draw both the initial and the final positions. Let me give you a little more help with this. What does this H stand for?
So now I totally got it. I didn't need to have MGH final because H final is 0.
That's right. So that's one thing. That's the hidden 0.
Yeah.
That would help us out. So one thing we could have done is that. But something else is, well, what does H stand for in this formula?
The height of the pendulum from...
Good. Now, in general, it stands for height.
Height.
Does this stand for height above the reference or height below the reference?
It depends on your reference. I think it's positive, so it should be above.
This is always the height above. That's right. I guess if you were below the reference, this would be negative. But as long as this stands for the height above. So it looks like there was something else that we did wrong, because I think for the initial point you said the height was 7. But that's a height below a reference.
I should do 12 minus 7 and get like, okay.
Yeah, so what should the initial height be?
5.
That's right. So this problem's a little trickier than the earlier one because I didn't quite give you the initial height. That's what I was trying to work out in my mind. I didn't work that out. But from these dimensions you can figure out the original height. Okay, so now we can go back and fix that work.
Okay, so. Here's this.
Good.
So I can draw it.
Should probably make it go down a little bit further. Oh, good. It's hard to draw. Good. Because it has to be falling in order to gain speed.
Okay, better. Oh, what did I do? Okay, so this is now 12 meter.
Because it's still the same string.
Yeah. And if this is 0,
We decided to say that the lowest point is the lowest point the pendulum reaches, not the ground. Good?
Yeah, that's what I meant.
Good.
It's not.
No, you did it correctly. Good.
Oh, okay. So when I do that, then I don't have this.
Good.
This is 0 too.
Good. That's one of those hidden zeros that's
Yeah.
important for us.
Then I can solve it easily. Just like multiply these and divide them by
Now, what are we
1.
plugging in for H initial?
Oh, yeah. I forgot this. It should be 5.
Good. Because 12 minus 7 is 5.
Yeah.
Good.
Yeah. So it will be square root of this. 1.8. Yeah, that's the same 9.9.
Oh, sorry. Okay, so what's the answer?
What was the question? Let me see. How fast is the pendulum moving when it reaches the vertical position? Yeah, that's how fast it is moving.
Okay, good. Okay, so let's review this here. Let's make sure we were systematic. One thing that we saw that is we need to be more careful about drawing both the initial and the final positions in the picture. That's always a good idea. I think we still haven't quite put an F in for the final position, so let's put that in the picture. So how would you describe those 2 points in words? The initial point was the instant the pendulum was released, and the final point is the instant it reaches the vertical position. We need to identify that in our head, even if we don't write it down. Also, it would be good to put down a question mark with the symbol for the question. That's always a good place to start.
Final.
The question mark. All right.
Sorry.
That's all right.
Takes time to get used to this. Be final.
Okay. Then you wrote down your general equation. That's good. You figured out all the individual types and you plugged in. So that was a good approach.
Okay.
Why did we get the same answer on this problem as the previous problem?
Because our mass was the same and the G is the same. Yeah, that's it. And in each position, in each side of the equation, we only had kinetic energy or potential energy. We didn't have both of them.
Good. Now, we haven't quite put our finger on the most important thing that's the same in these two pictures. I mean, it's not like all 3 kilogram pendulums always end up at the same speed as boxes. The key thing that's the same.
The distance from, the H is also 5 meters.
Yeah, that's the key thing that's the same. That's what I was spending so much time trying to work out. I wanted to make these similar because I wanted to show the exact setup doesn't matter. All that matters is that we're taking 5 meters of gravitational potential energy and turning it into kinetic energy. So it's important to see these really turned out to be the same thing. Here we're taking 5 meters of gravitational energy and turning it into kinetic energy, and here it wasn't as obvious, but we took 5 meters of gravitational energy and turned it into kinetic. If we had seen that, we wouldn't even have to have done the work. If you had seen that it was falling 5 meters, you could have just said, well, this is still the answer, basically. All right, it's good practice to go through it, but the point is, these are 2 ways that gravitational energy is tested. Objects moving on slopes and pendulums. And the lesson here is they're solved exactly the same way. The energy analysis is very similar, but these are 2 types of things that you might see on the test or on the homework. Okay, good. And we also saw how important it is to choose your 0 height. By the way, you could have said that the 0 height was the ground. Could you have done that? Actually, probably no, because there wasn't enough information to know where the ground was, actually. So, you probably could have chosen this as 0 height, but the problem would be considerably more complicated. So it made our life easier by calling this the 0 height.
If you had the distance of the ceiling from the ground, we could solve it.
That's right. Even without that, you can still solve it with algebra, but this is a lot simpler. This is a lot simpler. Okay, so here's another example. It would be good for you to go back and try again. I'll erase this now. All right. Okay, so let's try this one on the pad too. And again, I'll give you a chance to first work on this on your own. And if you get, of course, I'll give you some help. But try this first on your own and try to use the same types of techniques we were just using on the previous problems.
Okay. Okay, so it's going upward. That's okay. Okay, so we don't have the mass of the object. Do we need that? Oh, mass can cancel out. Oh, okay. Which might only be 2 over 9.8. meters.
Done?
Yeah.
Okay, so let's see. You drew a picture, that's good. I think you still haven't actually put in the I and the F for the initial and final position. That can help us to avoid mistakes. So put in a dot for the I and the F.
So this is I, this is F.
Yeah, we don't know exactly how high the final position is, but it's some unknown height up the hill. Good. So in words, the initial point is the instant it reaches the bottom of the hill.
Yeah.
And the final point is?
Somewhere on the hill.
Not any old somewhere. The final point is the instant it reaches the highest point on the hill. It's just important to be clear in your mind about that as the problems get harder. It's
but it reaches to V0. Actually, V equals 0.
Say again? Oh, so it'll be where V is 0. That's true. You use that when you solve the problem.
Yeah.
You put in HF was the question. That's good. You wrote your general equation. That's good. It looks like you assumed the initial potential energy was 0. That's okay because you chose the ground as height 0. And how did you know that the final kinetic energy would be 0?
Because when it reaches to that point, it stops for a brief moment, and that moment velocity is 0, so that makes the kinetic energy 0.
That's good. I would word that a little differently. Instead of saying that it stopped, I would just say the highest point is when it's changing direction. And since it's changing direction, the velocity is 0. But that's good. That gives people a lot of trouble in this. Often, notice the problem never said the final point had a 0 velocity. So that's something we need to realize.
Yeah.
Because the highest point you reach has to be when you're changing direction. So that's when your V is 0. So that's good that you put that in. Tell me, how did you get this line? HF equals 2 over 9.8. How did you get that from the previous line?
Oh, that's 64. I just divided 4. I didn't see 6.
Oh, yeah, it might be because of the pad.
64.
Okay. Yeah, so go back and try that again.
Yeah. So that's wrong. That's 64 divided by 2. It's 32 over 9.8. 9.8, which is 3.2.
Because otherwise it would only have gone 20 centimeters up.
Yeah. So 3.3 actually.
200
3.3
centimeters.
meters.
Okay. So. Okay, good. Okay, so we did better on this one than the previous problem. So this is just another variation. The key thing here was to see that the highest point is when you're changing direction, so the V is 0. Oh, there was another trick here. For a couple of seconds there, you were nervous because I didn't give you the mass. But you just kept working on it and you worked it out. So what do you do on the test if it seems like you're not given necessary information? Just use a variable, like you did. Just use a variable and hope it cancels out. And that's what happened. So this is interesting. We don't actually have to know the mass here.
Yeah.
This is related to the idea from kinematics that all objects fall at the same rate, regardless of their mass. This is a related idea that the mass of the object doesn't determine how high up the hill it's going to get. Okay, so,
That's because our surface is frictionless, right? Because if we had friction, then the mass matters, right? Or not?
Yes, that's true. If there were friction, the mass would matter. That is correct. That's not quite obvious, but that turns out to be true. Okay, so. So let's try this problem.
Okay. So the initial position is here. This is h equals 0. And this moment, the initial is 8 meters per second. And we want to know what vertical height does it reach as it slows. So it will go to this position, and we want to find this edge final. And this is initial, this is
Good, that's a good picture.
final. Okay. And so it has a velocity, that means the initial equal the final. The initial is 1/2 its mass 64 there's no potential energy, it's 0, because H is 0.
Because you chose that to be 0 height.
Yes. And then, as it swings by, it reaches at the point that it wants to change direction, so kinetic energy is also 0, kinetic energy final. So we only have potential energy, which is n, not G number, 9.8 H. These cancel out, H final.
Good.
So H final will be 32 over 9.8. Undo. H final is, what did we call 9.9? No, 3.3. Oh, no. This is not the square root, so. Yeah, 3.3. Oh, okay, never mind. 3.3 meters.
Okay, very good. The key thing is, how did you know the final kinetic energy would be 0? Because the highest height is when it's changing direction.
Right.
That's the hardest part for most people. The highest height is when it's changing direction, so V final is 0. Good. All right. Did you notice that this problem is the same as the previous one?
Yeah, pretty much.
So that, I just wanted to point out, doesn't make any difference whether you're working with a pendulum or an object that's moving on a slope. I purposely made these to come out the same. In fact, if we had seen that, we wouldn't have to do all that work.
Yeah.
If we had seen that this started with the same initial velocity, we could just say, I know for sure the answer will be the same. It's still good practice to go through it, but this problem has to give the same answer as the previous one because the velocity was the same initially in both cases. Okay, so the point is here, this has an initial kinetic energy of 1/2 m8 squared, and that's all going to turn into gravitational energy. And here it has an initial kinetic energy of 1/2 m8 squared, and that's all going to turn into potential energy. So those are the same, so they'll give us the same answer. So those are the two ways that gravitational energy is likely to be tested on the next exam, either with objects moving up and down slopes, or with objects on pendulums. And we can see it doesn't make much difference either way, it's the same general approach. Okay, so we've made some good progress on that. So now let's move on, because there's another type of potential energy besides gravitational potential energy. Do you know what the other type of potential energy is besides gravitational potential energy?
No. I was thinking that's the only one.
The other type is spring potential energy. And that's another thing that's probably going to be important on the next test is springs. So let's go on and add that to our list. So we also have, because I think we're getting the idea for the gravitational problems, so let's move on to the spring problems. So the next type is spring potential energy.
Okay.
What's a good symbol for potential energy?
U.
Right, but this one I'll call, now you can see why I called this GR, U, because I wanted to prepare ourselves for the other type of potential energy, which is spring potential energy. Okay. What do you think is the SI unit for spring potential energy?
Joules, the same.
And is it a vector or a scalar?
Scalar.
Because all types of energy have the same basic ideas. Good, so again we won't need axes or positive directions. Do you happen to know what the formula is for gravitational potential energy?
Is it 1/2 kx squared?
That is what it is. Very good.
Okay.
Okay. Do you get to bring a formula sheet to the test?
Yeah.
Okay, so we don't need to have that memorized, but we wouldn't have that on our formula sheet. Notice that it might help to remember that it looks kind of the same form as kinetic energy.
Mm-hmm.
Okay.
When do we have a negative sign next to k? I remember somewhere we have to put a negative sign there.
Sure. That's for spring force.
Oh, that's for the force. Oh yeah.
So we don't
right.
want to confuse spring
Always.
energy and spring force. That's a common mistake, so I'm glad that you brought that up. So notice, when we're using this framework, what equation would we use?
K, negative kx.
Good, but when we're using this framework, what equation do we use?
1/2 kx squared.
Yeah, so this is where it's helpful to realize there's two different frameworks with two different equations. Okay, good. Actually, my personal opinion is even with here, it's oftentimes better just to focus on the magnitude of the spring force and figure out the sign yourself. I don't know if you've seen in the videos, I like to use a dot when something's just a magnitude. So I personally prefer to use this formula and just figure out the sign myself. But it's true that the textbook formula here has a negative sign. Okay. But this formula definitely is always positive. All right. Now, do you know what the name of K is? What's the name of that constant?
Constant. It shows how tough, how stiff the spring is.
Good, that's right. The name is the spring constant. K is called the spring constant. Actually, let's go back to that formula you were mentioning. Good. And do you know what X stands for?
The distance that the spring is stretched or compressed.
Good. The distance from its natural length. So X is the displacement of the spring from the natural length. Good. So what would be the SI units for X?
Meter.
Good. So what are the SI units for K?
Since force is Newton meter, that should be Newton then?
Careful. What are the SI units for force?
Newton meter or?
No, actually, not quite. Think for a second. What are the SI units for force?
That's work. That's work.
Yes.
That is Newton meter. The force is just Newton.
Force is just newtons.
So,
that's right.
Yeah.
And what are the SI units for X?
Meter.
So what are the SI units for K?
Newton over meter.
Okay. So it's good to know that K is in newtons per meter. K is in newtons per meter. So what would it mean, say, if a spring had a spring constant of 5 newtons per meter? How would you interpret that in words?
It takes 5 newtons to move that spring, stretch it or compress it 1 meter.
That's a good answer.
From equilibrium.
That's a good answer. Great. So one thing that you did here is that you put a number on the bottom. What number did you put on the bottom?
1 meter.
Yes. So now you can say if you compress the spring 1 meter, that takes 5 newtons because it doesn't want to be compressed. Or to stretch the spring 1 meter takes 5 newtons of force because it doesn't want to be stretched. So how much force would it take to compress it 2 meters?
10.
Okay, so now we understand what this means. And so you're right, if you suppose you had K equals 100 newtons per meter, is this a stiffer or looser spring?
Stiffer.
So what you said before was right. The bigger K is, the stiffer the spring is. K measures how stiff or tight the spring is. This is harder to compress because now it takes 100 newtons to compress at 1 meter. So that's the basic intuition for what K stands for. That's good. So it's good to know the right units, newtons per meter. Okay. The natural length is where the spring would be if it's just resting with no outside forces on it at rest. This is where it wants to be. What would X be for the spring in this position? What would X? Okay, good. I was trying to trick you into saying 9, but you didn't fall for the trick. Good, but that's a common mistake. So notice X is not the length of the spring. X is not the length of the spring. It's, as you said before, it's the displacement from the natural length. That's important for solving problems. So that was right. You gave the right answer, 4 meters here. Good. What would X be for this position?
3 meters.
That's right. Not 2, because it's 3 meters for the natural length. Now, technically, this doesn't really matter too much. Technically, this would be -3, right? If we choose this as our positive direction, then this would be -3. But who cares? Because we're just, on these problems, we're just going to square it anyway, right? On these problems, we're just going to be squaring. So I'll just say the magnitude of x here is 3 meters, and the magnitude is 4 meters. For conservation of energy, it's just a useless complication to worry about the signs. So I'll use this dot to show we're just focusing on the magnitude here. All right, what's x at this point?
0.
That turns out to be very important. Good. So, what's the spring potential energy when the spring is at its natural length?
0.
Good. But that's important, right? Because we've seen how important it is to find the hidden zeros on these conservation of energy problems. We saw where the hidden zeros were when we're dealing with kinetic energy and gravitational energy. The hidden zero for spring problems is when it's at the natural length. Then the spring energy will be 0, because you don't plug in 5 for x. You just say it's 0 from its natural length. Okay, good. So x is not the length, it's the displacement from the natural length. Very good. Remember that when is the spring happiest?
When it's just in equilibrium.
Yeah, at the natural length. Good.
Yeah.
So should that be where potential energy is highest or lowest?
Lowest.
And that's working out, right?
Yeah.
So the lowest this can be is 0. Notice that it gets less and less happy the more and more you compress it. And that's reflected in the equation. So the equation makes sense. The more you are displaced from the natural length, the bigger the potential energy is, which reflects that the spring is less and less happy. It has more and more energy stored in it. It's more and more eager to get away from that position.
I like the happy and sad. I will never forget that.
Good, yeah. That actually turns out to be real helpful in science, because there's many cases in both chemistry and physics where things are trying to lower their potential energy. So it helps to personify them. Okay. So yeah, so this is a very unhappy spring that if you let go, it's going to be very eager to lower its potential energy from going back here, and the same for this one. Good. Something else that's worth thinking about is, let's see. Let's just continue here. Now there's two different types of, so in all of the problems that we do in this class, there's going to be a mass connected to the spring. Now, all the problems we do, the spring itself has no mass. Just like in this class we assume ropes have no mass, we're going to assume the spring has no mass. It's only this thing that has the mass. Then there's two different types of problem. We could do a problem where the mass was attached to the spring, so it can't leave it. Or we could do a problem where the mass is just touching the spring, so that it could theoretically leave it. Right now, we're going to deal with problems where the mass is only touching the spring. Later in the course, you'll deal with attachment. So let's say that we compress this spring, and we put the mass next to the spring, but it's only touching, it's not attached to it. What's going to happen when we let go of the spring? Which way will the spring move?
To the right.
Yeah, because the spring wants to push itself this way. It'll keep moving until it gets to the natural length. Does the spring want to move past the natural length?
Doesn't want to, but it does it until it just stops.
Well, let's think about that carefully. So the spring doesn't want to move past the natural length.
Yeah.
Now, the mass will keep moving anyway because of its inertia. Right? The mass will keep moving anyway because of its inertia. But remember, the spring has no inertia because we assumed it had no mass.
Oh yeah.
So this is when they will detach from each other. Once you get to the natural length, in this portion of the movement, the spring will be pushing the mass. But once we get to here, the spring is happy. There's no reason for it to move past the natural length. It wants to be at the natural length. So the mass will just keep moving away from it. That's why it's important to remember the mass is not attached, so it can't drag the spring with it. So when you compress the spring and you put a mass next to it, what happens? The spring will push the mass to the natural length, and then when you get to the natural length, the mass will detach from the spring. So that's important for the problems that we'll be doing here. Why does the mass keep moving even though nothing is pushing it? Because its inertia carries it forward. Why doesn't the spring's inertia carry it forward? Because we're assuming the spring has no mass. If the spring has no mass, it has no inertia. So it immediately comes to an immediate stop over here. Okay, so this is worth keeping in mind for the problems that we'll be working on. So when the mass detaches from the spring, when the mass detaches from the spring, what will be the spring potential energy? When the mass detaches from the spring, what will be the spring potential energy?
It will be 1/2 kx squared.
Good. Be more specific. When the mass detaches from the spring, what will be the spring potential energy?
What do you mean the...
When will the mass detach from the spring?
When the mass is attached, right?
So, when will the mass move away from the spring?
Oh, move away, so
That's
it's
what I mean.
zero. It's zero.
Yeah, because the mass will move away when the spring reaches the natural length. So let me ask you again, when will the mass move away from the spring? When the mass moves away from the spring, what's the spring potential energy?
Zero.
Zero. Good. That's the hidden zero that we're going to need for solving problems. Good. At this point, this is the point, say, that we're releasing the spring.
Mm-hmm.
What's the kinetic energy at this point when we release the spring?
That's 1/2 m3 squared.
Careful. What's the...
Sorry,
the point.
1/2 k 3 squared.
Let me help you a little. What's the kinetic energy when we release the spring from this point?
Kinetic energy is zero.
That's another hidden zero that we'll need. But what we're trying to do is see what are the hidden zeros we're going to need. So who's zero when we release the spring? Who will be zero when we release the spring?
Kinetic energy.
Because it's released from rest. And who will be zero when the mass leaves the spring?
The potential energy of the spring.
Because it'll leave when it reaches the natural length. So those are the zeros we'll need when we solve our problems.
Okay.
Good. And also, let's say that we have, let's say that later the mass hits this spring.
Mm-hmm.
This mass will hit the spring and it'll start compressing it until it reaches some maximum compression. What will be the kinetic energy when the spring reaches its maximum compression? What will be the kinetic energy when the spring reaches its maximum compression?
Zero.
Because it'll be changing direction there.
Yeah.
Maximum compression is when it's changing direction from compressing to expanding. So this is a little similar to the problems we did before. So there's another hidden zero. Over here I was telling you what happens when the mass is launched by a spring. And here I have an example where the mass is hitting the spring. So the point is when the mass hits the spring will compress, but it won't compress forever. It'll reach some maximum compression where it changes direction, and then the kinetic energy will be zero.
So does it mean as soon as the mass is hit the spring, at the moment of the impact, the spring has kinetic energy, but as the mass pushes more forward up to the point that it stops and wants to change direction, then the potential energy of the mass, spring has the potential energy, not kinetic energy anymore.
That sounds good.
Get it right?
That sounds good. So here's a mass that's moving towards the spring. Here's the first instant that the mass has hit the spring.
Okay.
What is the spring potential energy at this point? What's the spring potential energy at this point?
Zero.
Because we assumed that before it got hit, it was at the natural length.
Mm-hmm.
So the instant it gets hit, this is the hidden zero. The spring energy is zero. And then let's say this is the point of maximum compression. So what's the kinetic energy at this point?
1/2 kx squared. Oh,
what's the kinetic energy at the point of maximum compression?
Okay, kinetic is zero.
Yeah, because this is the point where it's changing direction.
Yeah.
It would be 1/2 mv squared, but v is going to be zero at this point. So at this point, the kinetic energy. So the point is, to prepare for our problems, we need to know when things are zero.
So kinetic energy for the spring is still the same, 1/2 mv squared, even though our spring is massless?
That's right. Well, technically the spring has no kinetic energy, but the mass that's hitting the spring has a kinetic energy. So that's whose kinetic energy we're looking at. We're looking at the kinetic energy of the mass that's touching the spring.
So the question will never ask the kinetic energy of the spring. It will ask the kinetic energy of the mass, right?
That's right.
Oh,
or it should, unless they're a little sloppy. But yeah, they should.
Okay.
That's right. So notice, that's a good point. Potential energy changes depending on what type of problem you're working on. But kinetic energy is always the same. It's always 1/2 mv squared. After all, we use the same kinetic energy for a slope that we did for a pendulum. That will be the same as the kinetic energy for a spring. That would be the same as the kinetic energy for a rocket or a car or a cheetah. Kinetic energy is always the same basic formula. Okay. Notice again that potential energy could also be called positional energy, because the energy here depends on your position in the spring.
Yeah.
Okay, very good.
2.1 meter per second. Hopefully that's right.
Okay, you drew a picture, that's good. Something that will help you going on though is specifically labeling the I and the F in your picture
So
as we get to harder problems.
initial position is here, a final position is perhaps here.
You could say that. It might be clearer though to say that the final position is what you've labeled as your equilibrium point, right? Because that's where it's actually going to move away from the spring. Now, if there's no friction, the speed will be the same at both of those points. But anyway, the final point is the instant it moves away from the spring is at the equilibrium point. Yeah. Okay. So in words, the initial point was the instant the spring was released, and the final point will be the instant the spring reaches its natural position. Because when the spring reaches its natural position, there's no reason for the spring to keep moving, and the object will separate and move away from the spring. Why does the object move away from the spring if the spring isn't pushing it anymore? Well, remember, an object in motion tends to remain in motion. So the object's inertia will keep it moving to the right, even when the spring's not pushing it anymore. But the spring doesn't have any inertia, because it has zero mass, because we just assume that. So the spring will stay behind at the natural length. That's what you used when you solved this problem. So you said that the initial kinetic energy was zero, because the spring is released from rest. We always assume that on spring problems. And you said the final spring energy was zero, because the object will separate from the spring at the natural length, as we talked about before. So that was the key. The final position is the natural length where they separate, so that's where the spring energy was zero. So you can see the method here turned out to be pretty similar to the gravity problems that we did before. This was a good systematic approach. Why don't we have to include gravitational energy? There's still gravity, so why don't we include gravitational energy?
Because it doesn't do any work on the system.
That doesn't quite explain it. Try again. Energy never does work.
Because
you're on the right track.
Because the object is moving horizontally, not vertically.
That's right. Why does that mean we can disregard the gravitational energy? It still can happen.
Because of this Newton's third law, the normal force of the surface is cancelling the gravity force.
Okay, that's not quite the key. There's a simpler way to put it here. What's the relationship between the original gravitational energy and the final gravitational energy?
Oh, they're constant.
They're the same. So they exist, but they'll cancel. So the point is, so if this was a vertical spring, you would have to include gravitational energy. If the spring was vertical, you would have to include gravitational energy, because then these would not be the same. So just because there's a spring doesn't mean we can automatically ignore gravity. However, it is true for any horizontal spring. For any horizontal spring, we can ignore gravity, not because the gravity doesn't exist, but because the gravitational energy will be the same on both sides.
So on the last problem that we were working on, the one that the object was going up the hill, so why didn't we consider gravitational force when the object was on the hill then?
Actually, we did. On that problem, we did solve it by using gravitational energy. After all, what else was there to use? Because there was no spring.
Yeah, we used
so,
MGH.
Yeah, so you were using gravitational energy on those problems. Right. So on these problems, you were using only gravitational energy and no spring energy. And then when we moved to this problem, you only included spring energy and no gravitational energy, and that was okay, but I just wanted to explain why it's okay. Because there is gravity, but the gravitational energy doesn't change for a horizontal spring, so those things will just cancel. Also, if we were going to include gravitational energy, we would probably say this is zero height, and then these two terms would be zero, which would make it even easier to see why they're going to cancel.
So if after the release, the object goes up a hill, then we have a potential energy of the gravity of the hill, but the initial is zero. Okay.
That's right. That's an excellent point. Okay. All right. So I'm not saying you made a mistake. It's fine to leave out gravitational energy for a horizontal spring. It's just good to know why we're leaving it out. Okay. Good.
Way better sense.
Okay. Good. So you solved that correctly. That's good. Oh, one interesting thing about that problem we just did. Remember that when we did the earlier problems about moving on a slope or a pendulum, it turned out I didn't have to tell you the mass.
Yeah.
So I just think it's a little bit interesting to see you do need to know the mass when there's a spring. Notice if I hadn't told you the mass, M would not have canceled here.
Yeah.
So for these problems, the mass does make a difference. Whereas for the earlier problems, we saw the mass didn't make a difference because it canceled. Let's try this problem.
So this is the initial position. So right here is the final position. And mass is 5 kilograms. Initial velocity is 1 second. And here is 1 So we'll do the same thing. E initial equal final. Okay. At the initial point is the moment of impact. We have 1/2 of 1/2 and v squared in the initial. Then press it, we have 1/2 kx squared. Yeah, and that's, yeah, okay. 1/2 times 5 times 60 equal 1/2 times 10 times x squared. X will be equal to square root of 40 over 5. 2.8 meter. Yeah, that's how much it will be compressed. Yeah.
Okay. Let's see. So you drew a picture, you labeled the initial and final points. That's good. How would you describe the initial point in words?
Initial point is the moment that the mass touches the spring.
Good.
But the spring is at the natural state.
Yeah, I didn't say that in the problem, but it's just common sense that before the spring gets hit, it would be resting at the natural state. That's why you said the initial spring energy was 0. Good. And then how would you describe the final point in words?
The final point is when the mass pushed the spring, compressed it, and...
You need to be a little more specific. The final point is when it reaches maximum compression, right?
Maximum, yeah.
Because over here it's compressed too, and over here it's compressed. But the final point we care about was the point of maximum compression, because the question was asking for how far does the spring compress at a maximum. All right, so the final point was the point of maximum compression. Why did you say the kinetic energy was 0 there?
Because the mass will have velocity of 0 due to change of direction.
Yeah, the point of maximum compression is where the spring is changing direction, so that would be a hidden 0. So the final kinetic energy was 0.
Yeah.
Good. Go ahead and use a question mark to write down the symbol for the question.
Oh, yeah. We are looking for the x. Okay. X final.
That's right. Okay, very good. Also, let me just point out a trick here. Can you see any way you could have simplified this equation before you started plugging in?
Oh yeah, I could cancel out the 1/2.
Okay, so just going forward, that's something you can do to make the math a little bit simpler, since you can't use a calculator on the test. Now, you can only do that if there's a 1/2 on both sides. You can't do that when you're using MGH. But when you're using these things, there's always going to be a 1/2, so you can make your life a little bit easier by canceling them. Okay, good. All right. That's how you do that. Very good. So what was the name of the framework that you used for this problem?
Conservation of mechanical energy.
That's right. So that's what we've been learning how to do. I think we made some good progress on that. This is one of the main new frameworks on the next midterm. Why couldn't you use these frameworks from the previous midterm? Well, remember that if you were going to use Newton's second law, you'd have to use this. But the spring energy will be constantly changing as it compresses. So there's no easy way to apply this formula here, because the spring energy will be increasing more and more the more it compresses. It would take calculus to analyze something with a constantly changing spring force. The bigger x becomes, the bigger the spring force will be. So this would be beyond our mathematical abilities right now to apply this. And for the same reason, since the spring force is constantly changing, the acceleration will be constantly changing. So we can't use kinematics, because our kinematics equations assume constant acceleration. So it's a good thing we've learned this new approach that can handle some problems that the previous approaches can't handle. Okay, good. We've seen this is the first key equation to write down. What does the E stand for?
Total initial mechanical energy.
That's right. And now we know what types of E do we have to plug in. Well, what are the types of E?
Kinetic energy, potential energy, gravitational potential energy, or spring potential energy.
So on any problem, you have to decide which of those are relevant. You have to decide which of the kinetic energy, the gravitational potential energy, and the spring potential energy will be relevant. Yeah. Good. Why did you decide that gravitational potential energy wouldn't affect the answer here?
Because it's the same on both sides of the equation.
Yeah, the gravitational energy could have been included, but it would just cancel because it's not changing in this problem. Very good. Okay, we had a little more time left, so I think we actually covered the parts of this that you're going to need for the next test. So let's just get a head start on the next framework. Do you know what the next framework the class covered was after conservation of mechanical energy?
Work.
Good, that's a good point. Now, work is really related to energy. So work and energy are work is an expanded version of this. Okay, and the fact is actually, work actually is on the homework a lot. It actually doesn't come up on exams too much. So let's pass over work for the time being. What's the next major framework you guys covered after energy? Momentum.
We covered, yeah.
So that's what I wanted to get a head start on now.
Oh yeah.
So the next framework is conservation of momentum. Okay, so we can get a start on that. So when we were working on these areas up here, let's see, one thing we had to do is we had to decide when we could use these approaches. When can you use this approach?
When we have constant acceleration.
Constant acceleration. When can you use this approach? Well, this is a little bit tricky. It mainly requires judgment when you can use this one. But we saw sometimes if the force is changing, it might be hard to use this approach. Okay. When do we use this approach? We didn't actually give you a very technical definition, but the key thing we said is if there's no friction, that's a good clue that you can use conservation of mechanical energy. And if there is friction, you could not use conservation of mechanical energy, generally speaking. When do we apply conservation of momentum for problems? There's one particular type of problem where we use conservation of momentum. I don't know if you picked up on this. When do you use conservation of momentum? For collisions. Yeah. Conservation of momentum is used for collisions. Okay, so that's a good thing to have down about this framework. It's used for collisions. It's also used for separations. Let me give you an example. So for example, if a firecracker explodes into 3 pieces, do you see why I would call that a separation? Because the 3 pieces separated from each other. So you could use conservation of momentum there. Or for example, let's say that I'm standing on the ice and I throw a baseball. That would be a separation because I've separated from a baseball. Or let's say that a gun shoots a bullet. Well, that would be a separation because the gun is separated from the bullet. So those are all cases that could be considered separations. Those are cases where you can oftentimes use conservation of momentum. However, actually that doesn't come up too much on exams. 95% of the time this is tested with collisions. So that's what we should mainly focus on.
Because he specifically, he covered gravity and then he switched to momentum and he said that don't worry much about gravity, but focus on momentum.
Okay, all right, so that's a good thing for us to talk about that. Okay. Well, when do we apply this framework? Collisions. That's the key first thing. That would be a good thing to have in your notes. Okay, so let's talk about this idea of momentum. Do you know what the symbol is for momentum?
P.
That's right. It would be nice if we could use m for momentum, but we're already using that for mass. So P doesn't seem very logical, but that's the symbol. All right, so do you know what's the formula that defines momentum?
mv.
Good. So momentum is a kind of measure of how much motion an object has. You could also think of it as this measures how hard it would be to stop the object. Because the faster it's moving, the harder it is to stop it, but also the more massive it is, the harder it is to stop it. So these two things together control how hard it would be to stop it. I kind of gave it away, but what does the M stand for?
Mass.
And what does the V stand for?
Velocity.
Very good. So what would be the SI units for momentum? There's no special name for these units, but we can figure out what the subunits are.
It's kilograms times meter per second.
Good. So we shouldn't have to memorize that if we know the formula.
Yeah.
Okay, so there's no special name for this unit like there is for energy. It's just subunits. Very good. Do you know, is momentum a vector or a scalar?
It should be a vector.
It is a vector. That's just part of its definition.
Yeah, because of velocity, it should be a vector.
So how is that important for solving problems? So does momentum have to be broken into components?
Yeah.
Because it's a vector. Unlike energy, where we didn't have components. And for momentum, do you need to choose axes in positive directions?
Yeah.
Yeah, because it's a vector. Now, I don't want to make too big a deal about that, though, because actually in this introductory class, you're almost always going to deal with simple one-dimensional problems for momentum. And when you're working in only one dimension, you don't have to be quite so careful about components, because there is only one component. But technically, this is a vector. Okay, so going back up to here, remember that when we learn each framework, we need to know what's the first general equation that we write down. For example, these were the first general equations for Newton's second law. We've learned that this is the first general equation for conservation of mechanical energy. What would be the first general equation for conservation of momentum?
P initial equal P final.
That's a good start. However, it really has to be sum of the P initial equals sum of the P finals. Because does conservation of momentum mean that nobody's momentum can change? No, it doesn't mean that. An object's momentum can change, but any momentum that one object loses has to be gained by the other object in the collision. So it's only the sum of the momentum that has to be constant. But what does conserved mean?
Constant.
Yeah. So this wouldn't be true, because this would make it seem like each individual momentum can't change. But then none of the objects could change their speed, and the problem would be very boring. So the individual momenta can change, the first object could start slowing down, but only if the other object speeds up. It's just like we saw up here for energy. It's possible to lose kinetic energy, but only if the gravitational energy, say, increases. So it's the same idea here. It's possible for object 1 to lose momentum, but only if object 2 gains momentum. That'll be clear when we do some problems. But it's just like up here, this is not a good version of Newton's second law, because this makes it seem like you only need to include one of the forces. No, you need to include all the forces. So that's all I mean by putting in the sum. I'm just saying you need to include all the objects in the equation, all the objects in the system. Okay, good.
One thing that's confusing with momentum for me, when we say if momentum of one object is lost, the other one should take that momentum. So when two cars crash, they pretty much stop. Their momentum is gone. So how do we explain that with this equation?
That's an excellent question. That's good. That's good that you're thinking about what it means instead of just trusting the equations. That's an excellent question. So let's say I have here, to make it simple, let's say this is 5 kilograms moving at 3 meters per second to the right. And here I have 5 kilograms moving at 3 meters per second to the left. So this is the before picture. So here's an example, kind of like what you were talking about. You were saying, suppose there's two objects that are rushing towards each other. Yeah. So it seems like they both have a lot of momentum up here. But after they hit each other, they'll just be at rest. Yeah. Now, how do we know they'll be at rest? Well, so far we just know it from common sense. Because the problem is symmetrical. Symmetry tells us they can't be moving left or right because they have the same mass and the same speed. So what you're saying is this seems to contradict conservation of momentum, because here they both had a lot of momentum, and here there's no momentum. So it seems like the momentum really has disappeared. Exactly. Well, the physicists can't have made a mistake, so we must be misunderstanding something. So let's see where our misunderstanding is coming from. The key is momentum a vector or a scalar?
Vector.
So do we need to choose positive directions and axes?
Yes.
That's the key thing you weren't doing in your mind when you thought about this. Let me show you that. So what do you want to choose as your positive direction?
Right.
That makes sense. So, what is the initial momentum of this object?
15 kilogram meters per second.
And what's the initial momentum of this object?
That would be negative.
Because
15.
That's right. So we should have said this initial momentum was positive 15 kilogram meters per second, because this velocity is positive and this velocity is negative. So notice that when you use this equation, you do have to plug in the sign of v. When you use this equation, you have to plug in the correct sign for v. If v is in the positive direction, the momentum is positive. But if v is in the negative direction, the momentum is negative. Okay. We haven't had to worry about that earlier today because so many of our v's were squared before. But now the sign matters. So this is what we could call, so we could say that P1 initial equals this, and P2 initial equals this. So what's the initial sum of the momentums?
0.
That's the key. So actually, there was no momentum in the system before. It seems like there's lots of momentum, but there's actually no momentum because the two momenta canceled each other out. Did this guy have momentum? Yes. Did this guy have momentum? Yes. But did the system have momentum? No, because the two momenta canceled each other out. So now let's check that over here. What's the momenta of this object now?
0.
Yeah. P2 final is 0. And what's P1 final? What's this object's momentum going to be?
0.
So what's the sum of the momenta going to be now?
0.
So the scientists are vindicated and the equation really did work. Because what was the sum of the initial momentums?
It was 0.
And what was the sum of the final momentums?
0.
Okay, so this equation really does work, but only if you remember that momentum is a vector and that the momenta can cancel each other out in the equation. This is why I made such a big deal about saying that we can't just use this equation. You can't just say, because was this momentum conserved? No, this momentum totally changed. It changed from 15 to 0. And was this momentum conserved? No, it changed too. It changed from negative 15 to 0. It's only the sum of the momentums that are going to be conserved. It's only the sum. So that's one of the keys to these problems, identifying all the objects in the system. You have to include all the objects in the system. Just like when you're using Newton's second law, you have to identify all the forces on the object.
What if we change the momentum of the objects on top?
How so?
Like give another mass or another velocity to one of them. So one of them is like negative 15, the other one is 20 or whatever, different. So then the system has a momentum, but at the bottom...
So we could try, say, this example.
Okay.
So now, what was this object's initial momentum?
20.
4 times 5 is 20. And what's this object's initial momentum?
Negative 50.
Same as before. So now what's the initial momentum total?
5.
Positive or negative?
Yeah, positive.
It's important to include the signs because we've seen. So overall, this now had a momentum. So this was positive 5 kilogram meters per second. Overall, this system is moving to the right.
Mm-hmm.
Part's moving to the left and part is moving to the right, but overall it's moving to the right because this had more momentum than this. Good. So, what's going to be the sum of the final momentum?
So after they crash, their sum will be 0.
Now, you're saying that they have to be at rest. But because this is not symmetric, they don't have to be at rest anymore. Just because two things have crashed into each other doesn't mean they stop moving. For example, if I'm running towards an elephant, do we come to rest when the elephant hits me? No, the elephant just keeps barreling right through me, right? So the object with more momentum will push the other one with it. That's right. So I think that was something else that was confusing you. Just because things collide doesn't mean they come to rest necessarily.
Okay, now it makes sense.
Yeah. Okay. So what we can say here is that so overall, once they collide, they've really turned into only one object. Now they've turned into one object. Which way will the object be moving now?
To the right.
Because overall the momentum was to the right before, so it has to continue to be the right here. In fact, we know what will be the sum of the final momentum.
Positive 5.
Because of conservation of momentum. So here we were using that these two sums have to equal. So these will both be positive 5. And now we can work this out. We can say that momentum final equals m final v final. We can make things simpler because there's really only one object after the collision. So what's going to be the final sum of the momenta?
Positive 5.
Good. What's our final mass?
It's 10.
Because these two things are together. If we're assuming they're sticking together in the collision. Now, objects don't always have to stick together in a collision, but if we assume they stick together, then we can say there's one object. And now we can figure out what the final velocity will be. It'll be just 0.5. And also notice, did this come out positive or negative?
Positive.
Which confirmed our common sense that they would be moving to the right afterwards. Okay, so the conservation momentum really does give us the right answer in this case too. So the two things that were confusing you a little were, first of all, I think you were forgetting that some of the original momentums could be negative, and some could be positive. And also, I think you might have been assuming that just because things stick together, they can't move anymore. But actually, if one of the objects started with more momentum than the other, it will push the other object in its direction. And that's what's happening here. Okay, but that's good. It's good that you asked that question rather than just taking this on faith. That's the way to build up some understanding and common sense so that the equation makes sense.
I had problems to get that good equation. I wasn't angry with it, so...
Yeah, okay. So it's good that you asked those questions. Hopefully now we have some more understanding. This equation actually does make good sense.
Yeah.
Now, the way that we did this is, we were working here on getting common sense and intuition. this is not the best way to do momentum problems. There's some shortcuts we can use for doing momentum problems, but this is a good way to start out with just to give us some intuition for what's happening in conservation of momentum, to convince ourselves that this equation really does make sense.
Yeah.
So we can see the key is don't leave out the summation sign. You have to include all of the momenta. It's only the sum that's going to be conserved. Once you have it copied down.
Okay.
So let's look at one more problem here. Okay, tell me when you have this written down. Okay, so now what? So what would be a good framework for attacking this problem?
Let me read it one more time. Oh, it sticks to a stationary object on the magnetic projection of the object's velocity after collision.
What would be a good framework for this problem?
So, for sure, conservation of momentum.
That's right, but how do you know? How do you know that conservation of momentum applies here?
Because two objects have a collision and then they stick together and keep moving. That's why we need the velocity.
Okay, that's good. That's good, but actually we could simplify it. It doesn't matter that they're sticking together. It doesn't matter that they keep moving. It's just because it's a collision. Any collision we can use conservation of momentum. Yeah. Any collision we can use conservation of momentum. The fact that they're sticking together is a detail, but that is not the key reason. It's just because it's a collision. Okay, so if we saw this problem on the test, we would know to use conservation of momentum. So one good place to start is to write our key framework equation. So what's the framework equation?
Sigma P initial equals sigma P final.
Very good. Now would be a good time to draw our pictures with our initial and our final points. Let me show you how I would draw that. I would say this is the initial picture. And this is the final picture. It's pretty simple. But notice you need two different pictures. You can't put them both in the same picture. It's well worth the time to actually draw the two pictures so that you're clear about this. So those are our two pictures. You can actually guess right now, and of course this object here was at rest. You can actually already guess which way will these objects be moving in the final position. Say again?
To the left.
You mean this way?
No, my left. That way.
Like this?
Yeah.
Really? So think again.
Oh, that was addressed. Sorry. I was only looking at the mass. Okay, no, to the right.
Because which way was the overall momentum before?
What's to the right?
Because this had a rightward momentum and this had no momentum. So the overall momentum afterwards should be to the right.
Should be the same, yeah.
So even without doing any math, we can guess that the answer is going to be to the right, or know that it's going to be to the right. All right. By the way, remember it's important to describe these points in words. So let me tell you how I would describe this. This is the initial point is the instant before the collision.
Okay.
And the final point is the instant after the collision.
The instant, okay.
This is the instant before the collision, this is the instant after the collision. Notice it's not useful to think about the instant of the collision. That's not useful for solving the problem. Instead of thinking of the instant of the collision, you need to think about the instant before the collision and the instant after. Otherwise, we won't have two different things to compare to each other. If you just think about the instant of the collision, then you only have one set of momentums. So when we're solving these problems, we compare the instant before the collision to the instant after the collision. Notice that those two instants are probably only separated by like a fraction of a second.
Yeah.
The whole collision takes maybe a tenth or a hundredth of a second.
I had a problem with that in my first exam because I thought that the question was not explained properly. So I pretty much had two solutions for the moment, for that very first moment, or like the moment after that. And I crossed one of them, so I figured, oh, okay, now I know what they meant.
Yeah, those are important things to think about. So anyway, for this type of problem, that's the way to think about it. This is the instant before the collision, this is the instant after the collision. What would be a good symbol for what this question is asking us?
So it is asking about the velocity v final.
That's better. We should choose a positive direction. So what would be our positive direction?
To the right.
Okay, good. So now plugging in here, the way I would write this is like this. This is the initial momentum of the first object. So what's the next term?
M2v2 initial.
Good. So notice there's a bunch of subscripts. We have to be careful with the subscripts. Now, this is a little tricky. What should I write over here?
So since they stick together, they are considered one mass, right?
Yeah, so we can just say how many objects are there after the collision?
M1 plus M2 times the V final.
Like this?
No, parentheses times V final.
Okay. So there's really only one object after the collision.
Yeah.
Now this is not true for all momentum problems, it's just because they happen to stick together in this problem. All right, very good. So then we can plug in, what do I plug in here? 2
times, what was the 10 meters per second.
Good, although it might be better to say positive 10.
Yeah,
good.
Positive 10. Plus
and what's this going to be?
3 kilograms times 0.
So I'll just say 0.
Yeah.
And then here we have
5 times V final.
Okay, good. So then we get
20 over 5, we get 4 meters per second.
Now, did that number come out positive or negative?
Positive.
Is that what we expected?
Yes.
If it had not come out positive, we would have known we made a mistake, because common sense told us it had to be moving to the right afterwards. How fast was this object moving before the collision?
10 meters per second.
Notice that they slowed down.
That's because the other object was addressed.
Yeah, so notice this, actually, that's something else we could have predicted. We could have predicted not only that they would be moving to the right, but they'd be moving to the right slower than 10 meters per second. They have the same momentum as before, but now more of the momentum is carried in the mass, so less of the momentum can be in the velocity. This should also just match your common sense. It makes sense that in order to get this object moving, we're going to have to slow down. So this object does match our common sense. So when we did the problem a second ago, I told you that the way that we did those earlier problems was a good way to build intuition, but not the best way to do a problem on the test. So this is the way to do the problems on the test. Notice this is pretty similar to how we did these problems here too. So it's the same basic framework. It's not surprising that it's similar because it's again conservation. We're saying that total initial equals total final. One thing that makes people make fewer mistakes is write down the general equations first before you plug in. Another thing that makes people make fewer mistakes is draw the initial and the final points. Otherwise people can get confused. That's an important thing to work on. Okay, so that would be our conservation of momentum. Okay, so there's certainly other things to cover for conservation of momentum, but that gives us a head start on how to do that type of problem. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. there's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.